see some example about diagonalizable minimal polynomial, about annihilating polynomial, about this concept, which had come in different type of exam. Because this type of idea I have told you, this is very important for any competitive exam. First, I will see one question which had come CSR Net December 2018 exam. The question is, consider a linear transformation T from Rn to Rn which satisfies T square equal to T minus identity. That means T square equal to T minus identity be the annihilating polynomial of this linear operator which is mapping from Rn to Rn, and from this expression we can write T square minus T equal to minus plus identity equal to 0. This is the annihilating polynomial of this linear operator which is defined from Rn to Rn. Option 1 has indicate T is invertible. Option 2 has indicate T has a real eigenvalue. Option 3 indicate T minus identity is not invertible. And option 4 indicate T cube equal to identity. Okay. Notice we can write the annihilating polynomial is such type x square minus x plus 1 equal to 0. Imply x equal to 1 plus minus root 3i over 2, and we all of us know minimal polynomial always divide the annihilating polynomial which is denoted as ax. That means minimal polynomial can be either, if we consider one root 1 plus root 3i over 2 equal to alpha, and other root 1 minus root 3i over 2 equal to beta, then mx would be either x minus alpha or x minus beta or x minus alpha times x minus beta. Okay, and we all of us know root of minimal polynomial always be root of characteristic polynomial. Characteristic polynomial. Okay, and notice here T be linear transformation from Rn to Rn. So root can be just, since here the linear transformation from Rn to Rn, root can be repeated, and since root are here non-zero, so obviously the T would be invertible, and all root are complex. So option 2 is a wrong option. T has a real eigenvalue. This is wrong option. And option 4 indicate T cube equal to identity. This option, since in the question has indicate T square equal to T minus identity, now multiply this equation by T, then this would be T cube equal to T square minus T. Now put the value of T square here, then this would be T minus identity minus T. Then this is equal to, just omit T in this equation, this would be minus identity. That means I have got T cube equal to minus identity. Okay. In the question has indicate T cube equal to not identity only, T cube equal to minus identity, and I have got T cube equal to minus in. So option 4 is the right option, and option 3 indicate T minus identity is not invertible. Since here I have got T square equal to T minus identity, So we can write t equal to t minus identity to the power half. Okay. Now apply determine both sides. Determinant of t equal to determinant of t minus identity to the power half, and since eigenvalue of t are both non-zero, so determinant of t are obviously non-zero, and since determinant of t non-zero, that implies determinant of t minus identity to the power half always would be non-zero, imply t minus identity is also invertible. Okay, and option 3 has indicated t minus identity is not invertible, so option 3 is a wrong option. Only option 1 and option 4 is a right option. Are you getting? Well, now I will discuss another interesting question. The question is, consider A be a 3 cross 3 matrix such that A square equal to minus I3, where obviously I3 means 3 cross 3 identity matrix. Then the matrix A is option 1 diagonalizable, option 2 orthogonal, option 3 does not exist, option 4 symmetry. Notice here A square equal to minus I3, that means A square plus I3 equal to 0. Obviously this would be annihilating polynomial. And we all of us know minimal polynomial always divide annihilating polynomial. That means if this is the annihilating polynomial, that means minimal polynomial can be x plus I or x minus I or x square plus 1. Okay, this is the possibility of minimal polynomial if this is annihilating polynomial. And we all of us know the root of the minimal polynomial always be the root of the characteristic polynomial. Notice in the question has indicated A be 3 cross 3 matrix. Since A be 3 cross 3 matrix, so always there exists one real root. Okay, this cannot be minimal polynomial because there exists no real root, because if there exists real root, then x minus alpha be one factor and alpha be any real number. That implies the matrix A, this type of matrix does not exist. Are you getting the idea? This is the right option. And other option, A is diagonalizable, this is wrong. Orthogonal, this is also wrong. Symmetric, this is also wrong. Only option 3 is a right option. Are you getting? I will say one question which had come CSR NET December 2018 exam. The question is, consider the matrix M whose entries are 1 minus 1 1, 2 1 4, minus 2 1 minus 4. And given that 1 is an eigenvalue of the matrix M, then which among the following are correct? Option 1, the minimal polynomial of the matrix M is x minus 1 times x plus 4. Option 2, the minimal polynomial of matrix M is x minus 1 whole square times x plus 4. Option 3, M is not diagonalizable. Option 4, M inverse equal to 1 over 4 times M plus 3i. For this, at first we have to find the characteristic polynomial. For this, to find the characteristic polynomial, we all of us know sum of the eigenvalue is trace of A and product of the eigenvalue is determinant of A. Consider lambda 1, lambda 2, lambda 3 are eigenvalue of the matrix M. That means lambda 1 plus lambda 2 plus lambda 3 equal to trace of A. And notice here trace means sum of the diagonal, and sum of the diagonal is 1, 1 minus 4. Since given 1 is an eigenvalue of the matrix M, so obviously lambda 1 would be 1. That means 1 plus lambda 2 plus lambda 3 equal to minus 2. That means lambda 2 plus lambda 3 equal to minus 3. And since product of eigenvalue is determinant of this matrix, that means lambda 1 times lambda 2 times lambda 3 equal to determinant of A. And since given 1 is an eigenvalue of the matrix, so 1 times lambda 2 times lambda 3 equal to determinant means just determinant of the M would be, just calculate, this would be minus 4. That means lambda 2 times lambda 3 equal to minus 4. And since lambda 2 plus lambda 3 equal to minus 3 and lambda 2 times lambda 3 equal to minus 4. So after solving, I will get lambda 2 equal to 1, lambda 3 equal to minus 4. When lambda 1 equal to 1, that means eigenvalue are 1, 1 and minus 4. The characteristic polynomial would be x minus 1 whole square times x plus 4. So, in the question has given about the minimal polynomial of this matrix M. Since the characteristic polynomial is this, so minimal polynomial can be either x minus 1 times x plus 4 or x minus 1 whole square times x plus 4. At first, calculate x minus 1 times x plus 4. That means calculate a minus identity times a plus 4i. And this would be a minus identity times a plus 4i. And after calculating, notice first entries would be minus 4. Then I will not do calculate other part, because this matrix cannot be zero matrix. So, since a minus I times a plus 4i not equal to zero matrix, so only possibility of minimal polynomial is x minus 1 whole square times x plus 4. This is other possibility of minimal polynomial. Okay. That means option 1 is a wrong option and option 2 is a right option, and option 3 indicate M is not diagonalizable. This is also right option, because here I have got minimal polynomial is x minus 1 whole square times x plus 4. This is not bilinear factor. So obviously M is not diagonalizable. And option 4 indicate M inverse equal to 1 over 4 times M plus 3i. That means for this, since characteristic polynomial of M is x minus 1 whole square times x plus 4, and by Cayley-Hamilton theorem, since every matrix satisfies the characteristic polynomial, therefore I will get by Cayley-Hamilton theorem phi m equal to 0. That means m minus identity whole square times m plus 4i equal to 0. That imply m cube plus 2m square minus 7m plus 4i equal to 0. That imply 4i equal to minus m cube minus 2m square plus 7m. Now multiply this equation by m inverse both sides. Then I will get m inverse equal to 1 over 4 times minus m square minus 2m plus 7i. And since m inverse equal to 1 over 4 times minus m square minus 2m plus 7i, that means option 4 is a wrong option, because in option 4 has indicate m inverse equal to 1 over 4 times m plus 3i. Are you getting? This type of question actually very important and very easy type question. But this type of question in every year for every competitive exam has come. Okay? Well. Next question is, which of the following statement is correct for every linear transformation? Next question is, which of the following statement is correct for every linear transformation? Here linear transformation is given as such type t from R3 through R3 such that t cube minus t square minus t plus identity equal to 0 operator. Option 1 indicate t is invertible as well as t is diagonalizable. Option 2 indicate t is invertible but not necessarily diagonalizable. Option 3 indicate t is diagonalizable but not necessarily invertible. Option 4 indicate none of this. Here the mapping t from R3 to R3, and the mapping is defined as t cube minus t square minus t plus identity equal to 0. For this, since we have to prove t is invertible, for this I will use just written this question. T square minus, here the annihilating polynomial is t cube minus t square minus t plus identity equal to 0 operator, and since we have to prove the operator t is invertible, that means we can write this as t cube minus t square minus t equal to minus identity, and now this would be t times t square minus t minus identity equal to minus identity, and this is, notice this is look like composition of two function, and when f composition g would be identity, then obviously g is 1 1 and f is on 2, and here this is look like composition of two function. Here composition of two function be identity, that means obviously t would be on 2 and this equation would be 1 1. Since the linear transformation t be on 2, therefore the matrix representation with respect to this operator, here all column would be, there exists pivot because t be on 2. That means obviously rank of this linear transformation, rank of this matrix would be obviously 3, because the linear operator t be here on 2. Okay? So obviously the operator t is invertible. That means that in the question has given t is invertible as well as diagonalizable. Option 2 indicate t is invertible but not necessarily diagonalizable. And option T is wrong option, because in the question has indicate t is diagonalizable but not necessarily invertible. Now I will see, is this operator be diagonalizable? For this, and since this is annihilate the operator t, so this is the annihilating polynomial which is x cube minus x square minus x minus 1 equal to 0. And we can write this as x square times x minus 1 minus, here given in the question plus identity, that means this would be plus 1 minus 1 times x minus 1 equal to 0. That means this would be x square minus 1 times x minus 1 equal to 0. This is the annihilating polynomial. And since minimal polynomial always divide annihilating polynomial, so possibility of minimal polynomial is either x minus 1 times x plus 1 or x minus 1 whole square times x plus 1. When the minimal polynomial would be x minus 1 times x plus 1, then t would be diagonalizable. Okay? And when minimal polynomial would be this equation, then we cannot tell t be diagonalizable. That means is diagonalizable. This is not necessary condition. That means option 2 is a right option. T is invertible but not necessarily diagonalizable, because option 1 is a wrong option. T is invertible as well as diagonalizable. Also option 4 is a wrong option. Okay? Well, I will stop here. In my next video I will discuss Jordan block of a matrix. This topic is very important for any competitive exam. Also, today's topic and today's question are very important for any competitive exam. So, I will highly recommend you. Please see today's video with pay attention. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for new videos. Thank you so much.